When confronted with massive, unlabeled datasets, we often need to force the data to reveal its own latent structure. Unsupervised learning gives us the mathematical tools to do exactly that. In Python's scikit-learn library, this process is frequently executed using the KMeans class. Calling the fit-predict method on this object triggers a specific hard clustering mathematical sequence. This scatterplot maps unlabeled bank customer data across two dimensions, income and debt. Our objective is to segment these customers. To do this, the algorithm minimizes the distance between every data point and the geometric centers of their assigned groups. That distance measurement constitutes the algorithm's loss function, formally known as inertia. Inertia is calculated as the sum of squared errors between the data points and their respective cluster centroids. To trust this algorithm in a production environment, you must deconstruct its underlying geometry, understand its objective function, and account for its initialization bottlenecks. Mastering these underlying mechanics bridges the gap between blindly calling an API and engineering a robust machine learning model. The standard engine driving KMeans is Lloyd's algorithm. It operates on a continuous two-step optimization loop known as expectation maximization. The process begins with an initialization phase. The engineer dictates the total number of clusters, denoted by the variable k. The algorithm then places exactly k centroids at completely random coordinates within the feature space. Next comes the expectation step, or assignment phase. The algorithm calculates the Euclidean distance, the straight line distance between 2 points, from every single unlabeled data point to each available centroid, assigning the point to the closest one. Following assignment is the maximization step, or the update phase. The algorithm calculates the exact mathematical mean of all the points within a newly formed cluster and physically shifts the centroid to that new geometric center. Because the centroids have moved, the distances to the data points have changed. The algorithm loops back to the expectation step, reassigning points to the newly shifted centroids, and then moves the centroids again. Throughout this loop, we track the model's inertia. As the centroids shift toward the true centers of data density, the sum of squared distances drops rapidly, eventually bottoming out as the system stabilizes. This loop halts based on strict mathematical stopping criteria. Either the centroids no longer move, points stop switching clusters, or the algorithm hits a hard-coded maximum number of iterations. By continuously alternating between calculating distances and shifting geometric centers, the expectation maximization loop forces the data to organize itself, relying purely on geometric centrality. Despite its efficiency, the standard Lloyd's algorithm harbors a critical mathematical vulnerability. The quality of its final output is entirely dependent on its initial, random starting state. If the initial centroids drop into poor positions, the algorithm can easily fall into a suboptimal local minimum. This is a mathematical state where the algorithm stops improving its loss function, but has failed to find the true best segmentation of the data. Consider a scenario with a poor random initialization. Two centroids land almost on top of each other inside a single dense cluster, while a third centroid lands far away in empty space. When the expectation maximization loop begins, it blindly follows its own rules. The two adjacent centroids awkwardly slice a single natural cluster in half, while the isolated centroid erroneously swallows the rest of the feature space. To a human observer, this segmentation is clearly incorrect, yet the tracking graph shows the inertia value flattening out. The algorithm has converged. It is mathematically stuck and cannot minimize the loss function any further. Relying on naive random initialization makes the algorithm mathematically fragile. It turns a deterministic optimization process into an unpredictable game of chance. To eliminate this initialization trap, scikit-learn utilizes a mathematical workaround called KMeans++. KMeans++ is a probabilistic seeding algorithm designed to optimally place initial centroids. Instead of placing all centroids at once, KMeans++ begins by picking exactly one starting centroid uniformly at random from the existing data points. It then calculates a metric called d of x squared. This represents the squared distance from that initial centroid to every other unlabeled data point in the feature space. This distance establishes a probabilistic seeding mechanism. The chance of a data point being selected as the next centroid is directly proportional to its squared distance from the closest existing centroid. Using this weighted probability distribution, the algorithm places the subsequent centroids. It recalculates the distances dynamically after every single placement. This mathematical constraint physically forces the initial centroids to spread out across the entire feature space, securing distinct dense regions before Lloyd's algorithm even begins. By replacing pure randomness with a distance-weighted probability distribution, KMeans++ guarantees competitive convergence and neutralizes the local minima trap. Even with optimized initialization, we still have to address a core limitation of KMeans. The hyperparameter K, the number of clusters, cannot be learned from the data. The engineer must define it a priori, before the algorithm executes. To find the optimal value, we plot the model's inertia against ascending values of K. This line chart shows K on the x-axis and inertia on the y-axis. The curve drops steeply at first, then flattens. We evaluate this chart using the elbow method. We look for the distinct elbow point where the sharp drop in inertia suddenly levels off, indicating diminishing mathematical returns for adding more clusters. You could continue increasing K to artificially force inertia to 0 by giving every single data point its own centroid, but doing so introduces severe computational costs and guarantees massive overfitting. Selecting the K value is a heuristic balance. You are constantly weighing the need to maximize intra-cluster cohesion against the critical need to maintain computational parsimony. Inertia is a useful metric, but it only measures the tightness of a cluster. That only satisfies half the requirement for a valid clustering model. The second requirement dictates that clusters must be mathematically distinct and isolated from one another. To evaluate this intercluster separation, we use the Dunn index, a formal metric for evaluating cluster validity. This cluster plot includes an overlay of the Dunn index formula. The numerator is the minimum intercluster distance, the shortest geometric distance between 2 points in different clusters. The denominator is the maximum intracluster distance, the absolute longest distance between 2 points within the same cluster. The evaluation goal is straightforward: maximize the Dunn index ratio. A higher score guarantees that the clusters are tight internally but remain far apart externally. Validating a cluster model requires moving beyond inertia. You must optimize for maximum internal cohesion and maximum external separation simultaneously. Even with optimized hyperparameters and validation metrics, KMeans operates on strict, hidden geometric assumptions. It assumes all clusters are perfectly spherical and shares similar point densities. This scatter plot illustrates a common failure mode: varying densities. We have one tightly packed cluster right next to a widely dispersed, loose cluster. KMeans incorrectly draws a rigid linear boundary cutting straight through the loose points. The algorithm misclassifies this data because it strictly optimizes for Euclidean centrality. It ignores the density of the data distribution entirely. A secondary failure mode occurs with varying cluster sizes. Here, the data contains one massive cluster and 2 tiny clusters. The centroids drag the boundary lines deep into the massive point cloud, misclassifying the outer edges of the large group. To protect against these geometric fragilities, the scikit-learn API relies on specific defaults. As seen in this code snippet, KMeans defaults to ninit equals auto and init equals KMeans++. The ninit equals auto parameter dynamically manages multiple random seeds in the background. It automatically runs the algorithm several times to ensure the best possible starting state is selected for the final model. Understanding the rigid geometry, the mathematical failure modes, and the API workarounds of KMeans is the true distinction between writing basic scripts and engineering reliable, production-ready machine learning systems.